So in this lecture, we're going to see a little bit more on the Hamilton's characteristic function. So I briefly introduced it before we solved the linear harmonic oscillator problem. So we're going to see a little bit more on the Hamilton's characteristic function. So we had said that we started out with the Hamilton's principal function, which was of course a function of Q's. So this was the generating function for the Hamilton-Jacobi theory, and we have when the Hamiltonian, right? So when the Hamiltonian does not explicitly depend on time, so h is not a function of time. Then what happens to the S, the Hamilton's characteristic, Hamilton's principal function? It splits into W, just Q and P, and minus AT. So we have this W we had called as the Hamilton's characteristic function. So this is what we had called as the Hamilton's characteristic function. Hamilton's characteristic function. So the new p's, right? The new p's and the q's in the Hamilton-Jacobi theory are all constant. So we know that. So we can replace by the constant alpha and by the constant alpha here again. So we know that the Hamilton's principal function generates these transformations, right? So P is equal to ds by dq. And similarly, the Hamilton's characteristic function also generates similar transformations. So here we have P is also equal to dw by dq. And Q, we in the principal function is related, generates this kind of a transformation. And here the Hamilton's characteristic function also generates similar transformation. So notice, however, we had got a constant, right? So last time we had got that h is a constant because it is not a function of time. So we had got that we had got the constant. We had got it as a constant alpha in the linear harmonic oscillator problem. We had got h as a constant alpha. So let me go to the next page probably. So we had got h, and when we were solving the linear harmonic oscillator problem, we had got h as a constant alpha, right? Remember that. So we can switch back and forth between these videos and probably just look on them. Or I would advise, since this entire thing might be a little confusing, you might have probably you could also have a textbook, right, with you to see the lectures in along with the textbook, so that you can go back and forth, right? So in the linear harmonic oscillator problem, we had got h as a constant alpha. Now, where are all these constants coming from? So we remember this was our in the Hamilton-Jacobi theory. This was the relationship between the old and the new Hamiltonian. The generating function f2 was generating this transformation. F2 is nothing but the Hamilton's principal function. So this is a function of q's, capital P and T, right? Remember that. Now we, of course, we are demanding that in the Hamilton-Jacobi theory that k is 0, right? That's why we get both alpha and beta, the new momenta and new coordinate, to be constant. Now let's take this to be, now we are writing only one generalized coordinate. Let us take this to be about n generalized coordinates. Is going up to n, okay? And therefore the new momenta, right? So P, so it will also have the P is alpha, right? So they are constants in the new momenta are constants. So alpha 1, alpha 2 is going up to En, or let me write it as P1, 1, P2. They're all going up to N, and we have T. Let me write it in terms of alpha. So, notice that this is a differential equation, partial differential equation uh, of S in n plus 1 variables, right? So here we have n plus 1 variables. So when you solve this partial differential equations, you will get n plus 1 constants, right? Constants of integration or integration constants, you will get that many constants. So these are the constants which we are interpreting as the momenta and the constant Hamiltonian, right? So these integration constants only we are interpreting as these new momenta, transform momenta, which are constant, and one of the integration constant we are interpreting as the constant energy or the Hamiltonian. So this is where it is coming from. So again, I'm saying all this could be a little confusing. So if you have a textbook along with what these lectures, you can go back and forth between the Hamilton Jacobi theory or the canonical transformation, and the Hamilton's principal function, characteristic function, and check up all these things so that you're not lost. Okay, so anyway, so now see, these things are these constants of integration we are interpreting as the momenta. So now when we have, so what are our equations of motion for, now we are talking about the equations of motion for the Hamilton's characteristic function, right? So now we are discussing the Hamilton's characteristic function. Now we're going to talk about the equations of motion here. So when we're talking about the equations of motion, we have P dot, so capital P dot is equal to minus dk by dq, right? So this is nothing but Hamilton's equations of motion, right? So these are the Hamilton's equations of motion that I'm writing out. Okay, sorry, excuse me. Let me add some new slides. Okay, so we're ready to go. Sorry about that. So we have Q dot dk by dp, right? So these are the Hamilton's equations of motion. Now notice here the Hamiltonian H is a constant. It does not depend on time. So the transformation generated by W now will be such that K, the new Hamiltonian, is also a constant, the same constant K alpha, because it is not a function of time at all, right? So it will be the same Hamiltonian, because in this in the transformation generated by Hamilton's characteristic function W uh, corresponds to a Hamiltonian that does not depend on time. So therefore, both the new and the old Hamiltonians will be the same. So we have for P dot dk, which is a constant differentiated with respect to q, will be 0. Okay, so this will be 0, and this is dk by dp. Now p, notice p is nothing but the alpha itself, right? So p is the new conjugate momenta, which is a constant alpha, right? So therefore uh, k is also alpha, p is also alpha. So dx, let's say dx by dx will be what? It will just be 1, right? So it will just be 1. So this will be 1. However, we can do something here. Sometimes what is done is, so here this is alpha, right? So let me write it down. So sometimes these constants that are coming out of, so these constants, right? So we have these constants alpha, alpha 1, alpha 2, alpha 3. They can be grouped together as a function. Okay, so sometimes, so this alpha, so is this gamma can be a function of alphas, so the integration constant that we get, because sometimes the integration constant, a group of integration constants will correspond to the new conjugate momentum. So therefore, now this equation then will then be, so gamma will be, so here this equation reads like, we are differentiating now this k also now will become functions of gamma. Okay, so this k is also a function of gammas then. So k is also a function of gammas. Okay, so k is a function of these gammas. So gamma. So therefore, this equation is nothing but we are differentiating. It is like differentiating f of x with respect to dx, right? So that is what is happening here. Okay. So when you do that, you get f dash of x, which is a new function of x, right? So I get a new function of these gammas, which I will call as nu. Okay. Nu. So that is what we get. So now we can say q is, so q dot is nu. So q is nu times t plus an integration constant beta. So that is what we got. So all what I've been saying now is very specially significant for one case of a problem where we have periodic motion. Okay, so we have periodic motion and total Hamiltonian. So we have periodic motion and the total energy of the system is a constant. So the Hamiltonian, which is the functions of q and p, is a constant, and therefore p can be written as a function of q's and alpha. So now we're going to introduce a new variable. So we're going to introduce a new variable. We're going to call it j. This has, you can see from the definition itself, it has the dimensions of angular momentum, because this is p dot dq, where so angular momentum is moment of linear momentum. So linear momentum multiplied into with dq, right? So we, this is integrated over the complete period. Okay, so the closed loop integral integrated over the period. So this is a periodic motion. So this has dimensions of angular momentum, and you can see from this equation that uh, h, right? So h, which is equal to alpha, is going to be only a function of j. So this is by virtue of the fact of this equation and the fact that this is periodic motion where you integrate between the periods, right? So you integrate a closed integral between the upper and the lower limit is the uh, period, right? So it's the period where the repetition of motion is happening. So this is by virtue of that. So now we have the Hamilton's characteristic function. Then in this case would be, so W would be, generally W we said is a function of Q and P's, right? So P, now instead of P we have J, right? So W was a function of Q and alpha, right? Capital P, right? So W was a function of capital P. So we had W was a function of Q and capital P. Now we're going to say it's a function of J because this is the momentum variable here, angular momentum. And we had this transformation equation, right? So we said Q and we had this transformation equation. So now this transformation equation is going to read this way. Now we're going to introduce a variable W, small w, again confusing terms. So this is capital W, this is small w, and or let me call it some other variable. Let me call it uh, okay. Okay, let me stick to the notation here that is given. So let me call it W, small w. So here we're going to introduce this variable W variable that is corresponding to Q, and that would be now dW by dJ. So you can see why that is from this equation itself. Here you have Q, here you have W, here you have P, here you have J. Okay, so this W is going to be called as the angle variable. Angle variable. So writing it out, and this capital W. Okay, this capital W is the Hamilton's characteristic function. So do not get confused. So what would our equation of motion read? So we just said that, here you saw that the equation of motion, Q dot, right? So instead of Q dot, we have W now, and instead of the new momenta P, which we wrote as the constants alpha, we grouped them and wrote it as gamma. So instead of that, we have J here. So what we have is W dot, small w dot is equal to H J, right? So this is going to be some function mu J, right? So this is what we wrote here. So remember, this new. So this new has a specific interpretation here in this case as the frequency. So that is why we were developing that theory so long. So this new has this. So if you now this W angle variable, if you integrate it, you will get more W is equal to mu T plus integration constant beta. And this new here has the interpretation of frequency. So this W is called the angle variable, and this J is called the action variable. Okay, so this names that you might find useful to remember. Sorry about that. So action variable. So this is what we got. So we've discussed a lot of things, and as I said, go through the videos with probably a textbook along. It will be helpful. And if you have doubts and comments, you can post them in the comment section. If there are a lot of doubts, I'd probably do another video to help you out. So if you found this helpful, do subscribe. That will encourage us to do more videos like this, and do share with your friends so that they are also benefited from this. Thank you for watching.